What if the universe wasn't a giant rubber ball, but a vast black hole with a radius of tens of billions of light years? We've struggled for thousands of years to understand where this chaotic and immense mass of matter comes from. In this video, I want you to let go of familiar concepts and theorems because the truth is, humanity is on the verge of finding answers to the most puzzling questions. The Big Bang Theory might be wrong, and we could be just a speck of matter inside a supermassive black hole. Join us on a daring journey as we explore a mind-boggling question. Could humans truly exist inside a black hole? This is EYES 200M, a scientific channel delving into the profound mysteries of the universe. The idea that our entire current universe is a bizarre point deep inside a black hole might sound a bit crazy, but it's not entirely unfounded. Going back to the time before the Big Bang, quantum physics believed that all matter we see today was compressed into a point with infinite density. This infinite point is described much like a bizarre point inside a black hole, which we can now observe. Scientists have a perfect picture of the early universe known as the Big Bang Theory. In this model, a long time ago, the universe was much smaller, much hotter and denser than it is today. About 3.8 billion years ago, during the primordial period, everything that makes up who we are today was formed within the first few minutes of the universe's existence. And all of this came from a tiny, compact ball with infinite density, about the size of a peach, and a temperature of over 1,000,000 trillion degrees. The idea of a universe arising from nothingness may sound incredibly crazy, but the evidence for it is quite convincing. Galaxies are moving away from each other, like pieces of shrapnel from an exploded shell, and the lingering heat from the Big Bang is still present all around us. Although it has cooled significantly due to the expansion of the universe, this afterglow doesn't appear as visible light. Instead, it mainly exists as microwave radiation, the cosmic microwave background radiation, which was discovered by radio astronomers way back in 1965. Astronomers have done everything from observing the leftover electromagnetic radiation of the early universe to measuring the abundance of the lightest elements. And they have found that all these observations align with the predictions of the Big Bang Theory. As far as we can tell, this is an accurate portrait of our early universe. However, the Big Bang picture is still incomplete. There is a missing puzzle piece. This missing piece consists of the earliest moments of the universe, and it remains a significant mystery. The problem here is that the laws of physics we use to understand the early universe are a surprisingly complex mixture of general relativity and high-energy particle physics. However, they can only take us up to a certain limit before a breakdown occurs. As quantum physicists attempt to delve deeper into the very early moments of the universe, mathematics becomes increasingly convoluted. If we try to resolve it, the complexity only grows until everything reaches a dead end. Therefore, the answer to the question, what was the universe like before the Big Bang, still lacks a reasonable solution. However, right now, I can present to you a rather attractive hypothetical answer. Let's embark on a journey back to the time before the formation of the bizarre point from the Big Bang and explore what truly happened. We'll also examine whether our current universe could be a world inside a black hole. Don't worry about doubting the accuracy of the Big Bang, because we won't be focusing on it. Instead, we'll delve deep into the cosmic string theory. The cosmic string theory is one of the prominent theories concerning the origin and evolution of the universe. It proposes that before the Big Bang, our universe was not a singular point of beginning, but part of a continuous sequence of universes existing within an endless chain. This hypothesis was proposed by the American astronomer and physicist Alan Guth in the 1980s. He developed this theory to address certain questions that the Big Bang Theory encountered, such as why the universe exhibits such perfect symmetry or why it has a spherical shape, meaning it is not contracting due to the gravitational pull of objects. According to the cosmic string theory, before the event of the Big Bang, there was no space, time, or universe as we currently know it. Instead, everything existed in an incredibly tiny and extremely hot collapsed state, also known as a singularity. At the moment of the Big Bang, a very powerful event occurred, known as inflation, causing space and time to start expanding rapidly and exponentially. The inflation period we know of lasted for an incredibly short duration, only around 10 to the power of minus 36 to 10 to the power of minus 32 seconds after the Big Bang. During this period, space expanded rapidly and suddenly, causing the universe to grow very quickly, leading to the uniformity and symmetry we observe today. It also explains why the universe has a spherical shape, since magnetic pressure opposed gravity, pulling the universe into a spherical form during this phase. However, instead of stopping after some time, like in the traditional Big Bang theory, the cosmic string theory suggests that the expansion never halted and continues infinitely. Throughout this expansion, each new universe is continuously and cyclically spawned from the universe before it. Each new universe may have different characteristics and conditions, but they all still adhere to the general laws of physics. According to this hypothesis, our universe is one of these universes in the endless chain. Although the cosmic string theory proposes a chain of universes, each universe exists independently and does not directly affect or interact with others within our observable range. As a result, we cannot directly observe or interact with other universes in this chain. Alan Guth's theory shares many similarities with the theory of black holes that we are currently studying. In both cases, the Big Bang represents the bizarre point of the universe. The bizarre point and the process of developing baby universes mentioned in the cosmic string theory share striking similarities with what humans assume about black holes. In space, when stars and galaxies operate under the influence of gravitational waves, we know that enigmatic events like black holes may hide extra dimensions of space. That's why entities beyond the event horizon cannot study the bizarre point inside. It's akin to a black hole limiting our understanding of the bizarre point by its event horizon. The reason for this hypothesis is the gravitational force inside a black hole. We all know that nothing can escape the immense gravitational pull of a black hole, not even light. So, if you were to take a journey inside a black hole, it could be a one-way ticket forever. Now, you might be wondering how this concerns our main topic of discussion. Well, let's imagine you are sitting on a spaceship and slowly moving toward the event horizon of a black hole. Essentially, a black hole is imagined to be like a funnel with an infinite depth. If you travel from the mouth to the bottom of the funnel, you will only see everything within the radius of the funnel's mouth. The same principle applies to our universe as well. Observations and estimates indicate that the current radius of our universe falls within approximately 46 to 47 billion light-years. Beyond this boundary, we cannot observe anything further. It could be empty, or there could exist a void separating different universes. Sounds crazy, doesn't it? This is the first similarity I want to share with you. The simple structure of a black hole consists of two parts, the event horizon and the spatial singularity. The event horizon is the boundary of the imaginary space. When any matter or light crosses this boundary, it gets pulled and sucked inward by a heavily curved space, making it impossible to escape. If an object falls into the region of the event horizon, nothing can prevent it from falling inside the black hole. The same principle applies to our universe as well. Essentially, the universe expands indefinitely and continually propels forward, causing everything to be unable to escape its radius. When observing it visually, we cannot precisely conclude whether the universe is expanding or galaxies are falling towards the bizarre point of this gigantic funnel. This situation is somewhat similar to Galileo's story about whether the Earth revolves around the Sun or the Sun revolves around the Earth. To provide more accurate evidence on this matter, we have the theory of cosmic microwave background, abbreviated as CMB. It is a concept in astronomy related to observing and studying cosmic microwave radiation. The CMB, cosmic microwave background, is light emitted from the distant and early stages of the universe. It is generated from atoms formed in the present-day universe, allowing light to freely travel through space. Before that, the universe was a hot, dense plasma that emitted random light. However, as atoms formed, the plasma became more transparent, and it no longer absorbed and emitted light randomly. The CMB is observed as microwave radiation with a very low temperature spectrum, approximately 2.7 Kelvin. That's about negative 270.45 degrees Celsius. This is the leftover light from the closest time to the history of the universe, after the Big Bang, and we can see it in all directions across the sky. The boundary of the CMB marks the limit of the universe. Beyond it, space cannot escape. The similarity between CMB and the event horizon lies in both being boundary lines in space and time. The CMB serves as the boundary for light in the universe, where light cannot escape the universe but can move freely through space. The event horizon is the boundary of a black hole, where space is so curved that nothing can escape beyond it. Both are related to the expansion and structure of space and time in the universe. Thus, when considering it visually, the idea that our universe is a world generated inside a black hole is not entirely unreasonable or illogical. On the other hand, both CMB and the event horizon play important roles in the study of the origin and evolution of the universe. CMB is one of the most crucial pieces of evidence for the Big Bang model, helping us understand more about the state of the universe shortly after its formation. Meanwhile, the event horizon of a black hole is the point in space where nothing can escape, and it is vital to understanding the nature and influence of black holes in space and time. Both serve as significant milestones marking the end of time. We cannot observe any events occurring beyond those horizons. Event horizons and the boundaries of the universe are not the only points of similarity. If we set aside other complex principles, we find another intriguing similarity between the singularity of a black hole's core and the singularity right before the Big Bang. Both are singular points with infinite density, occupying the entire space. The only difference is that the singularity of the Big Bang exists in the past and encompasses the entire space, while the singularity of a black hole exists in the future with the entire black hole space. If you find this a bit difficult to grasp, let's delve deep into geodesic incompleteness to enhance our understanding. According to the theory of general relativity, objects not under the influence of forces will follow something called a geodesic. In Riemannian geometry, a geodesic is the shortest path between 2 points on a curved space with uneven shapes and curvatures, such as a concave or flat curved space. In a sense, geodesics form a grid that defines the structure of space-time. They will extend infinitely until they are forced to terminate at some point. According to this theory, all geodesics will never end, except at singular points. This state is referred to as a geodesic incompleteness. Geodesic incompleteness refers to the situation when a space has some geodesics, or shortest paths between 2 points, that cannot extend infinitely, but must terminate at a limited point after a finite time. It is often related to the existence of a region in space-time where geodesics cannot continue indefinitely, but only exist for a finite duration or end of a specific point, such as a singularity. This can occur when space-time has uneven concave or flat curvatures and is influenced by an extremely strong gravitational force. In reality, in the theory of general relativity, singular points are defined as the end point of geodesics. All geodesics in the universe come together and terminate at the Big Bang. We call the Big Bang a singularity because it represents the end point of space-time in the past, as it occupies the entire past space-time. A black hole contains a singularity like a space-time endpoint in the future. It has the opposite direction compared to the model of the universe's formation according to the Big Bang theory. This is the second similarity I want to share with you. That means all geodesics within the space-time of a black hole will also terminate at the singularity in the future. It is a process where matter is completely broken down and compressed at the singularity. Since a black hole is an infinite entity, the question of whether you would be crushed by a black hole remains unanswered. The singularity of a black hole is the future endpoint that encompasses the entire space-time existing below the event horizon, just like how the Big Bang is the past endpoint that encompasses everything outside. When comparing the two shapes, you will notice that they are very similar, with the only difference being their orientation. Black holes point toward the future, while the Big Bang points towards the past. Black holes are like small universes embedded within a larger universe. They are like universes within universes, similar to the description provided by the cosmic string theory that I presented to you earlier. Now, what if we flip the black hole? Could it become a model for our universe? This is the hypothetical concept of black holes and white holes presented in the theory of general relativity. We will make the model of a black hole look like our present-day universe by synchronizing the theorems and mathematical laws inside the black hole of the universe. How can we do this? First, let's send a singularity into the past to create a black hole with time reversed. You might be familiar with or have heard of this model. It's called a white hole, an exceptional solution to Einstein's equations. A white hole was first discovered through coordinate transformations in Carl Schwarzschild's OG black hole solution. In the 1960s and 1970s, scientists like John Archibald Wheeler, Robert Oppenheimer, and Kip Thorne significantly contributed to studying black holes and the concept of white holes. They analyzed and explored the properties and structures of black holes and proposed the idea of the existence of white holes. A white hole is described as a region of space-time where energy and matter cannot enter but can only leave. Similar to a black hole, a white hole has an extremely short gravitational field, but instead of absorbing everything into it, it emits everything from the inside out. If we only consider their shapes, the universe and a white hole look quite similar as they both originate from a singularity in the past and release matter from inside. However, from the mathematical and quantum physics perspective, a white hole is a realm of pure space-time. It represents an absolute case of space-time, and light escapes from every point within the white hole. A white hole is considered the opposite of a black hole due to its contrasting characteristics. Inside a black hole, nothing can escape from the region known as the event horizon, whereas inside a white hole, nothing can enter the region called the horizon, and everything can only escape outwards. This operation is similar to the Big Bang, as no matter can pass through the event horizon of a white hole. If instead of a black hole, our universe was a white hole, the newly discovered matter and young galaxies by James Webb would have answers. However, the nature of a white hole is not analogous to our universe. Compared to the universe, a white hole contains no ordinary matter. It consists of absolute space-time and an uneven distribution. As you move closer to the singularity of a white hole, the curvature becomes stronger and more unstable. White holes exhibit very strong tidal forces. If an object like a star gets close to a white hole, these tidal forces can stretch and tear it apart in a process known as spaghettification, where the object is elongated into a thin shape along the direction of the tidal forces. On the other hand, the universe has a relatively uniform distribution of matter and energy, and as you move closer to the Big Bang, the density and energy distribution become more uniform. Throughout its history, the universe has had nearly flat space-time curvature. As a result, it doesn't generate the powerful and frightening tidal forces seen in white holes. This is the most significant difference that prevents the universe from originating from a white hole. Returning to the idea that humans might be living inside the world of a black hole, what would happen if every black hole absorbed enough matter and space and then underwent a Big Bang-like explosion? This is the starting point of Lee Smolin's theory of natural selection in the universe. According to Smolin's theory of natural selection in the universe, the cosmos contains numerous different physical systems, and each of these systems has the potential to create new universe offspring through reproduction processes. In these processes, the characteristics or attributes of the parent universe can be inherited or modified in the offspring universes. In simpler terms, the theory of natural selection in the universe suggests that there are many different offspring universes, each with varying traits and influenced by natural forces like gravity, environmental conditions, and interactions with other universes. Throughout the process of evolution, the offspring universes that have more suitable characteristics to survive and thrive will continue to exist and develop. According to this theory, these selected offspring universes become the dominant ones at a certain point in time, and their existence and stability are achieved through the process of natural selection. Unsuitable or unstable universes will gradually be eliminated or not last for a long time. This is why our universe appears perfect and capable of supporting life. The energy and matter density are finely tuned, and even a slight deviation could lead to the destruction of an entire universe. However, to gather a large number of samples for the selection process, it would require a vast amount of black holes. Returning to the theory of universe selection, Lee Smolin initiated the idea of allowing multiple offspring universes, each with different characteristics and attributes. This suggests that there could be various types of black holes with different features and properties. If we consider black holes as a reproductive system, there may be different variations of black holes existing in the universe. From this diversity, we can hypothesize that there might have been billions of offspring universes with different constants due to the existence of distant black holes within the same reference framework. In essence, the theory of natural selection not only assesses the possibility of a universe's existence, but also opens the door for deeper studies into the evolutionary mechanisms of the universe and the diversity of physical systems. It provides a new and unique approach to viewing the universe as a dynamic and evolving system, helping us better understand the formation and evolution of the universe in the past, present, and future. But it doesn't stop there. Lee Smolin's natural selection theory also leads to another fascinating concept known as the multiverse and the technique of traversing through multiple different universes. According to a controversial hypothesis, wormholes could exist somewhere in the Milky Way, connecting to an entirely different universe. In physics, a wormhole or Einstein-Rosen bridge is a hypothetical tunnel-like structure in space-time that creates a shortcut in space-time. They connect one space-time region to another, and sometimes matter can travel from one region to another by passing through this tunnel. Many theories have emerged since the theory of relativity appeared, reshaping the fundamental framework of modern physics. Several astronomers speculate that a wormhole could be formed by combining a black hole with a white hole. Furthermore, according to a recently published hypothesis in the Annals of Physics, it follows the discovery of a supermassive black hole at the center of our galaxy. Some experts propose that the black hole might be a kind of wormhole. A wormhole is considered to be a structure in space-time that resembles a tube, connecting two different points in space and/or time. Think of it as a shortcut in space-time, allowing an object to travel quickly from one point to another without traversing the vast distance between them. However, to sustain a wormhole and prevent its collapse, it would require a type of exotic matter known as negative matter, with properties opposite to the ordinary visible matter. This exotic matter would need to generate negative spatial pressures to keep the wormhole stable. Based on intricate mathematical models, Professor Pablo Sallusi from the International School for Advanced Studies in Trieste, Italy, suggests that this hypothetical tunnel, if it exists, could potentially be constructed using dark matter. Dark matter is an invisible and mysterious form of matter believed to make up about 26% of the universe. Researchers have combined the map of dark matter in our galaxy with the most recent Big Bang model to explain the universe. What we have found is that our galaxy could indeed contain one of these tunnel-like structures, and that tunnel could be as large as the size of the galaxy itself, says Professor Sallusi. Furthermore, he believes that in the future, humanity might be able to travel through these shortcuts to reach completely different space-time locations. The team led by Professor Sallusi emphasizes that their research results are incredibly significant as they confirm the potential existence of wormholes in most spiral galaxies. Dark matter could provide the energy for the formation and maintenance of these wormholes. According to Einstein's theory, any real wormhole would be like tiny rips in the fabric of space-time. However, Professor Sallusi suggests that these wormholes might be lurking at the center of large spiral galaxies, big enough to swallow entire spaceships. Experts believe that other spiral galaxies, such as the Andromeda galaxy, could also harbor wormholes. In theory, we could test this idea by comparing our galaxy to a nearby peculiar galaxy, such as the Magellanic Clouds, for example. The research is based on a similar report from last year conducted by physicists at the University of Cambridge, where they argue that certain wormholes could potentially remain open for a sufficient amount of time to send messages backward in time or to the future. My calculations show that if a wormhole is much longer than it is wide, you could create negative energy in the center of the wormhole, meaning it would take a considerable amount of time for the wormhole to collapse, according to Professor Luke Butcher from the UK University. And because the wormhole's ends could exist at different points in time, if Professor Butcher's hypothesis is correct, we could theoretically send a message through time. Returning to our initial topic of discussion, if the universe is indeed inside a black hole, and we assume that we have undergone billions of selection processes to become the most perfect model of creation, the search for life beyond Earth will expand significantly. Humanity has only recently begun the endeavor to seek life within its own universe. In the future, as our cosmic civilization advances, could we venture to seek similar life in neighboring universes? Many believe that attempting to traverse a black hole would result in crushing destruction. but it might be easier with supermassive black holes. At the center of these immense black holes, as large as a galaxy, the flow of matter is slower and gentler than in young black holes. If fortunate, we might cross that event horizon and explore whether there are any worlds within the black hole. There will be many new stories written in the future. We might encounter our own duplicates through different dimensions. Nowadays, such theories are still classified as science fiction, but I believe that in the not-so-distant future, humanity will achieve that feat. However, this remains a distant prospect, heavily reliant on the advancement of cosmic technology for centuries to come. Today's video will pause here, but don't forget, there are still many mysteries in the future waiting to be discovered. As Lee Smolin once said, quote, "The universe is not a place, it's a way of being," end quote. So we will continue to live, exist, and learn from the universes and black holes in our lives. Thank you for joining us on this journey. See you in the next videos with many other fascinating topics. Don't forget to like and subscribe to not miss out on the latest content from our channel. Wishing you fantastic explorations of the universe and black holes. See you again.